Welcome to Study Loop.
Okay, we have got this reaction XBr2 gas going to X gas plus Br2. So it's a dissociation of one molecule into two. We're told that the initial concentration of XBr2 is equal to 2.00 moles per liter. And we're told that the system was allowed to react and come to equilibrium, and that Kc was 4.0 times 10. I'm assuming this is 10 to the 8th. The caret didn't show up. But the question is, what's the concentration of Xg at equilibrium? Okay. We can pretty much figure this out with an ice table. Okay. May not be entirely necessary, but it will help show where the numbers are coming from, right? So I like to show the reaction again at the top of my ice table. Okay. And I like to say, okay, initially, what was the concentration of XBr2? We had 2.00 moles per liter, 0x, 0Br. What was the change, right? So the change is where this is kind of the confusing part. We don't know what the change is. We just put a variable in here, x, and we say that we're going to lose x moles per liter of XBr2, and we're going to gain, right, because for every 1 mole of XBr2, we gain 1 mole of X and 1 mole of Br2. Okay. So we're going to gain X moles of X. I really hate. Let's not use the letter X here. That's unfortunate. Let's use, what's a good, let's use Z. No, Z looks like 2 and kind of like 7. Let's do A. I'm going to lose A moles per liter. Okay, so we're going to have positive A here and positive A here. And so at equilibrium, we're going to have 2.00. And this is where we basically just take I and we subtract C from it. I minus C equals E. 2, or I guess I'll say plus. It's really plus. Minus A. And then here we're just going to have A. And here we're just going to have A. Okay. So now we need to recall the equation for the equilibrium constant. Kc, in terms of concentration, is going to equal the concentration of the products at equilibrium, raised to their stoichiometric coefficients, which in this case is 1. So we can basically ignore that. The product of the concentrations of the products over the product of the concentration of the reactants. We've only got one reactant, XBr2, also raised to its stoichiometric coefficient, which is just 1. And finally, we can just plug in these values, right? So this is a concentration. This is a concentration. And in fact, it's the concentration at equilibrium. Great. Okay, so let's plug those in. I see A times A over 2.00 minus A. Right? That's what I see. Let's rewrite this as, now recall that we know what Kc is. They told us it's 4.0 times 10 to the 8th, and that's equal to what looks like a squared over 2.00 minus a. And what we need to do, right, what the question is what's the concentration of Xg at equilibrium, right? Let's not lose sight of that. We're looking for this number, the concentration of X at equilibrium, which is right here, which is just equal to A. So we need to solve for A. That's the whole point of this down here. We need to solve for A. And we can do that with algebra. We're going to multiply both sides by 2.00 minus A. 2.00 minus A. So these will cancel. And we'll get 4.00 times, so just 10, times 10 to the 8th times 2.00 minus A equals A squared. And we'll get 2.00 times 4.0, that's going to be 8.0 times 10 to the 8th, right? Do that multiplication, FOIL it out. Minus 4.0a equals a squared. Oh, I made a mistake there. 4.0 times 10 to the 8th a equals a squared. And then we subtract a squared from both sides because we are going to turn this into a quadratic equation so we can solve for a. All right, so we're going to get negative a squared minus 4.0 times 10 to the 8th a plus 8.0 times 10 to the 8th equals 0. And if you recall the quadratic equation, the root of this equation, right, when does this equation equal 0, is going to be negative b squared plus or minus the square root of 4ac over 2a. Sorry, I'm not going to use capital for lowercase ac over 2a. Is that right? I haven't used the quadratic equation in literally maybe a decade or a half. Quadratic formula. Nope, I did this way wrong. Apologies, it's been a while. Okay. So the answer we're going to get is A equals negative b plus or minus the square root of b squared minus 4ac over 2a. And what the heck are a, b, and c? Where did those come from? They're the coefficients on the squared term for a, the linear term for a, and the constant for a. So in this case, the coefficient in front of a squared, little a, is equal to negative 1. The coefficient in front of a here is negative, so little b equals negative 4.0 times 10 to the 8th. And the coefficient c is just 8.0 times 10 to the 8th. Okay, so we plug all of that into this calculator, and we get the following. Now, we should get a negative root, which is meaningless and is really, really big, and that's using this minus here, but the other root is going to give us about 2. This is going to give us 2, basically, 2.00000, and when we finish sig figs, that's just 2.00, or 2.0, right? Does that make sense? I think it makes sense. Recall that we were told that Kc, right, this is an equilibrium, is really big. It's 4 with 8 zeros after it. That means that in terms of this reaction, it's favored heavily, let's see, 100 million. We should have 100 million times more X than we do XBr, right? So if we started with 2 moles of XBr and our equilibrium concentration tells us all of it's going to convert to X because the equilibrium constant is so huge, then we should expect to get roughly 2 whole moles of X, because we get 1 mole of X for every 1 mole of XBr2. Right. So that is a reasonable answer. It's basically just 2. This, we could have maybe answered this without even thinking about it, that this is such a huge number that implies all of our XBr2 is going to convert into X and Br2. Right? We expect to have 4.0 within a small margin of error. We expect to have 4 with 1, 2, 3, 4, 5, 6, 7, 8. So what is that? 400 million molecules of X for every 1 molecule of XBr2 when we're done. So yeah, it makes sense that we basically just get 2 moles per liter.